All right, welcome, Quiz 3 review. So let's go through it quickly. Just a brief overview of all the topics, what's on it, and then we'll do a sample question from the final exam from 2016 or something like that, which will probably be much more difficult than what's actually on the quiz. So the quiz will probably be difficulty and distance-wise, or length-wise, probably be between quiz 1 and 2. So quiz 2 didn't have very many questions, and it was kind of brutally long. The questions that were given, and quiz 1 was really, really short, so this one will be somewhere in between. So it's going to cover 4 general topics: scheduling, page replacement, page tables, and the TLB, so the translation look-aside buffer, and general virtual memory questions, a slew of true, false, or multiple choice ones. So there won't be any sockets or anything like that because that's what we went over recently. So just to remind you, scheduling, that's the thing that had a bunch of trade-offs. We saw non-preemptive ones, which you probably are pretty lame to ask on a quiz, like first come, first serve, or shortest job first. Then we saw 2 main ones when we had preemption, so we could change what process is currently running. We can context switch to it at will. We saw shortest remaining time first, which optimizes the lowest waiting time, but has an issue with starvation. So you should know what starvation is, where a process might not be scheduled because other processes are already shorter or something like that, and a long-running process may never be scheduled. Then we saw round robin. Everyone was really, really bored. Everyone seemed to get it. So won't go over, but it might be like, hey, here's some processes. What's the schedule? Then we saw even more scheduling algorithms. The most you would see on the quiz is like we went over that dynamic priority scheduling example. So that's another thing of, hey, here's some processes, which one's running. Other than that, it's fairly general stuff. So like, you know, some processes, there's no one good scheduling algorithm. Different processes need different things. So if you are interacting with the process, you want good interactivity, good response time. If it's just a batch process doing some computations, you don't care. You want to process as many of them as possible in a given time, so you might care more about reducing the waiting time there, and those 2 things are definitely at odds with each other. So there's going to be no perfect solution. We saw real time, all the difficulties that come up if we have multi-processor systems. So either we have a big global queue and have to do locks, or we have different scheduling algorithms for each individual CPU. Then we saw, ideally it's fair. That's the idea behind the completely fair scheduler that's actually used in the Linux kernel, but the Linux kernel stuff, you're not going to have to do scheduling that the Linux kernel does on a quiz or something like that. So then we went into page tables. Page tables just translate virtual to physical addresses. So we'll have an example today that will be harder than probably what would be on the quiz. Modulo, maybe we use multi-level page tables on a quiz. Cough, cough. But for page tables, what you do, so there's the MMU, that's the memory management unit, that's the hardware that uses page tables and does the translation. So we could have either a single large page table, which may be wasteful because it would have to be able to hold all the entries for every single possible virtual address, and processes, unless you know your Chrome or VS Code or something like that, you're not going to use all the virtual addresses. So most processes don't actually need all those entries, so a lot of it is actually wasted space. So we looked at multi-level page tables to save space. Idea behind them was each smaller table fit exactly on a page, and then we just followed it however many levels we need to in order to find the allocation. So we need, to resolve one address, we need to have at least 1 page table for every single level to resolve 1 single address, which is still going to be way less memory than every single possibility. And then if you're the kernel, you only allocate pages or at memory in pages, and you could do it with a simple free list or something like that. And the TLB is just the translation look-aside buffer. It's basically the cache from virtual addresses to physical addresses, and we'll have a question at the end to see if we understand that. Then we did page replacement. Everyone was really, really bored about this. Hopefully everyone can do this. So given some page accesses, what are all the faults? That is a perfectly valid quiz question. It's like the algorithms you could do optimal. So, you know, you replace the page that's used less in the future to get the most amount of essentially accesses that are still in memory. Then random, that obviously wouldn't be on the quiz because how the hell are we going to mark that? And then FIFO, so that's easy to implement, first in, first out. And then that had that weird anomaly where we had less memory and also less page faults. Pretty much the only thing you care about in page replacement is minimizing the number of page faults. So that was a weird thing with FIFO. And then we saw least recently used, which gets close to optimal, expensive to implement, but for the purposes of the quiz, you could probably do it. Yeah.
So like, are we allowed to use that clock algorithm?
Yeah, so I don't think the other course actually went over the clock algorithm, so there's probably not going to be a question of like, hey, here is a schedule using a clock algorithm, tell me the number of page faults. So I don't think the other section 1 never did it.
Wait, but isn't the clock algorithm replacement algorithm technically?
So the clock algorithm is like, it's in the idea of least recently used, but it's not exactly least recently used. It's an approximation.
So it's like during a quiz, we'll just be like saying, you just have to say I'm using this algorithm specifically.
Well, for the quiz, it'll be like, hey, what are all the, tell me all the page faults if I use least recently used. Or tell me all the page faults if I use optimal. Tell me all the page faults if I use FIFO.
Oh, okay. So it's not like you choose yourself like what to do.
Yeah, I don't think we have enough TA hours to do that. So, yeah, so it wouldn't be something like that. Something mean to waste your time would be like, hey, do this for all different algorithms and tell me the answer, but like optimal is going to be better. Yeah.
Is it going to be like quiz 1 where there's more multiple choice and stuff, or is it going to be like quiz 2 where it's more like written?
It's going to be in between. So there's going to be at least, you know, a big page table question and probably a big scheduling or page replacement question, and then a bunch of more multiple choices. So, and the multiple choice won't be essentially a long answer problem. So either 2 or 3 long answers. So scheduling, page replacement, they're kind of the same boring thing. We kind of know how to do them, and then probably page tables. And we'll see a page table question. And yeah, just for giving terms to stuff, so pages, when it's on disk, typically it goes into something called a swap file. So that's a name you might run into in the multiple choice. So a bitmap is basically, yeah.
Sorry, back to the swap file. So if it's on a disk, a page is called a swap file.
So all the pages on disk are in a big swap file.
Okay.
And the swap file is what holds all the pages on disk. Yeah.
You have to know, like, isn't there like a frame and a page? Like a frame is the physical page and the page is a page.
Yeah, so frame, physical page, page typically means virtual page. You could call it physical page, you could call it physical frame, you could call it frame. They essentially all mean the same thing. In the context of the question, you should understand what it's talking about, but you might see different terminology. And yeah, so quickly, bitmap, so it's what slab allocators use. It's what anything that allocates of a fixed size use. Just to be more explicit, the bitmap itself is going to be a contiguous block of memory that tracks slots. So however many bits you have is however many slots you can track. For example, if you have a bitmap that is 512 bytes, well, 512 bytes times 8, that is 4,096 bits. So you could keep track of 4,096 slots. So bit 500 would be slot 500, and you could do the math. So if you wanted to check what bit 500 was, you could see what byte you need to check by just dividing by 8, and then you take the remainder to see what bit you have to check, and that's how that works. Okay, Coremap we didn't talk about, and they didn't talk too much into detail of it, but it's a data structure you should know. Basically, it just manages the physical pages or frames, again, interchangeable. So it keeps track of what processes are accessing what frames, mostly in order to actually deallocate it properly. So because we have two processes and we could have shared memory, so two processes could be sharing the same physical frame from their own different virtual addresses. So you have to keep track of how many processes are actually referencing a frame. And that the Coremap is the data structure that does that. So each frame would track what processes are pointing to it, and when you deallocate it, that process would no longer be pointing to it. And if no processes are no longer pointing to it, then you can finally deallocate it if you're the kernel. Yep.
Normally you're only going to have one process pointing to a
Yeah.
single frame, right?
Yeah.
So the only difference would be like if you do that weird special fork where you like technically share resources or something like that?
Yeah, so this would happen on forks. This would happen, like you'd be sharing pages on forks. You could explicitly share pages to do shared memory, but we haven't seen how to do that, but it's not out of the realm of possibility where two things could map to the same frame and then actually share memory without doing that copy on write thing. Yeah.
So will format just be like a hash table, except it's like the value would just be like a list of all the virtual process that's like addresses that map to it?
Yeah, it could be a hash table. It could be whatever.
One way to go the other way around, right?
Yeah, it's just figuring out, given a frame, what processes are pointing to it. Yeah, okay, so here's other things that might appear in the multiple choice and good things to know. So rough latencies. So CPU cache will be nanoseconds. Memory is like hundreds of nanoseconds or a microsecond, which is 1,000 times slower. An SSD, which I think the quiz is old, so they don't know what an SSD is. But that would take like double-digit microseconds, and then disks or hard drive, like the spinning things, would take up to milliseconds. So that's why doing page replacement is bad, and it's so slow because it would take milliseconds, which is like a factor of a lot different. Yeah.
The CPU cache is the TLB, right?
So there's a lot of cache. For doing the translation, the cache is called the TLB. But like there's caches for memory, like your L1 cache and your L2 cache on the CPU, which doesn't quite correspond to the L1 and L2 page tables, but that's a different thing, just to make life confusing. But that's like cache on your actual CPU. But the only number, if you get into the multiple choice and it's like, hey, how slow is something? It's probably asking about a disk, and it's probably milliseconds. So that's a good number to know. All right, last thing I didn't touch on, but we kind of talked about it a little bit, is spatial versus temporal locality. And spatial locality just means accesses are close together in memory. So they'd be contiguous or almost. So if two memory accesses, if two pieces of memory are accessed together, hopefully they are located together. So they would at least be on the same page, if not contiguous. And that way you only have to do one virtual memory to physical translation, and then there'd be a cache hit, and it would be in the TLB. So every other time you access either address, it would be cached. It would be nice and fast. So that's just each other in terms of space. Then the other is temporal locality. It's being accesses close to each other in terms of time. So if two accesses are close to each other in terms of time, they're kind of related somehow, and you would want them to also be located close together to be really fast, but they're two separate things. So things could be accessed close together in time but not located together, and things could be located together but not accessed at the same time. Ideally, you would want things to be, everything that is accessed together at the same time is close together, but they're two different things. Okay, so we didn't give this a name, but we kind of talked about it. So thrashing is when there's a high number of page faults. So when a process cannot have their working set in memory, and a working set is just the amount of memory a process needs to execute without any page faults at given some like short time interval. So it's just how much memory it needs in order to actually run successfully without hitting any more page faults. So if your working set wouldn't fit in memory, it means that under normal execution, that you would have a page fault, and then you would have to do page replacement, which would go to disk, which would be really, really slow. So if a process is constantly evicting pages, it's going to be really, really slow, and it's something you don't want. So if you're the kernel, you can kind of detect this by keeping track of the ratio of page faults. And if it gets too high, maybe you just go ahead and deallocate memory from another process and pick a page from another process in order to give more memory to this current process that's trying to execute, because it needs more memory, and you actually want to clear it up a little bit, give it more memory so its working set can fit into memory, and it's not constantly swapping out to disk all the time. So the kernel could do something like that. But you might see the term working set on the quiz. Okay, demand paging. This is another thing that we didn't give a name to that we just kind of talked about. So this is the idea of doing things lazily. So whenever you start a process or something like that, you would assign all the you'd set up all the page tables with all the virtual addresses, but they wouldn't actually go to physical memory yet until their first access. So if you're the kernel on the first access, then you would allocate an actual page, and then you would modify the page table entry to make it point to that newly allocated page. So the flip side of this is if I didn't have this, I would have to allocate all the memory for the process as soon as it starts and allocate all of it, even though it might not ever use it. And also that would be really, really slow for starting up. So then kernel can go ahead, page fault, figure out, back it by an actual page. And then during this too, it might not always back it by a physical page if you're doing demand paging, because that process, as we've all done before, could just access any old virtual address that isn't actually valid to access. And then when it gets a page fault, it would just send a seg fault back up to that process, and then we get our fun seg fault we've got. So that's it for demand paging. And then we have copy on write, and then we'll go into our example, which will take most of the class. So copy on write, we've talked about. This is just to make sure we get it. So the idea behind this, you can also do other interesting things, is same idea with data races. If there's only reads to pages, then we're allowed to share them as many times as we like. There's essentially no data races. Everything can be shared for free. So when we fork, two processes can share the same frame and then either could write to them, but again, by default, we want things to be independent. So if you're the kernel, you could go ahead, have them share the same frame, and then if either process tries to write to it, then you'd essentially turn the write permission off so you get a page fault, so then you can service it. So when you see that, you would then, and only then, copy the actual physical memory of the page and have one page with the modification mapped to the process that made the modification. Then you leave the other page alone, and now the other process can go ahead and write to it later if it wants to. So this can also have some optimizations with read-only frames if we're doing page replacement. So for example, assume that our process is running, it's executing some code, it's only reading code over and over again. So it would be loaded into memory, it would be loaded into a page, and then maybe we decide to evict that page that just has code that's being read. Well, it's a bit of a waste of time to write it back out onto disk when that actually already exists in disk somewhere where that original file was. So instead of writing that essentially read-only page back to disk, or write it back out to disk only to read out some information that's elsewhere anyways, I can just go ahead and reuse that page, and then I can just go ahead, if I need to use that or swap that page back into disk, I'll just reread that file again from disk since it's there anyways. Yeah. Yeah, this is only possible if it's a read-only page. Otherwise, it would have modifications, and then you actually have to write it back out to disk if that's your only copy of it. Okay, so this is what will take a long time. So this question is a bit weird and will take most of the class. So This is a bit of a weird one because it talks about tag TLBs, which we talked about briefly, but this is a full example of it. And a tag TLB just means that, so every process has its own virtual address range. So in the TLB, there's also a spot where you can attach the process ID that virtual address is valid for. So let's go ahead and read this question. So we have an early 16-bit processor, uses a single level page table. That's a slight sigh of relief. That's not a multi-level page table, but you should probably be prepared for one of those. But anyways, for this single level page table with 250 byte pages, so anytime I see some numbers, good practice is to just write the equivalent power of 2, just in case. So what's 256 in powers of 2? Oh no, 8, to the 8. So luckily that's the same as a byte, to the 8. So it's the number of values you could have it in a byte, so to the 8. So maximum amount of physical memory it can support is to the 16. So now we know how big our physical frame number is. So this is how many bytes are on a machine. So we have a 16-bit address here. So then it shows us the TLB and the page table entry have the following format. In the TLB, there is the virtual page number, and then essentially after it is the page table entry. And here we're used to seeing PPN, like physical page number. This is just PFN, which is physical frame number. Means the same thing. So there is in the page table entry, there is a physical frame number, there's a process ID, and then there are 4 bits. There is a bit that says if it's in swap, and if it's in swap, the physical frame number should be interpreted as a swap location. And it only looks at it as the valid bit is 0. So there's also a valid bit, a reference bit, or sorry, not a reference bit. Oh, there is a reference bit, but it's not used. Oh, sorry. So a reference bit is just if it's currently referenced in the TLB, we actually won't use it in this. It just lets you know that that entry has been referenced before. So that it's actually backed by a page, so it could be valid, but not actually referenced. So it could be a valid virtual address, but it doesn't actually point to a physical page yet, so you need to fix it up. But don't worry, the reference bit's not here. So all we care about is in the page table entry, there's 4 bits here. In the TLB, there's 4 bits here. So it's just 4 bits of space. Okay. First question is, calculate the maximum number of processes whose page table entries may exist in the tag TLB at a time, which is other words of saying, how big is this process ID in terms of bits? So we have to do some math here. So we have to figure out how big the physical frame number is in terms of bits. Anyone hazard a guess as to how big that is? So this machine has 16-bit addresses, and the page size is 256 bytes. So if we write out an address, it would be offset, and then our physical frame number if this was a physical address. So how many bits are in our offset? 8 bits. The total thing on this machine is 16 bits. So how big is the physical frame number? 8 bits. 256, oh no. So it's just 8 bits.
What is it, 8 bits minus 4? Or do you not count as the 4 bits for the reference?
What? No, we're just figuring out how big the physical frame number is without looking at anything else. So the physical frame number, it takes up 8 bits. So now we can go back, yeah.
Is the offset equal to the page size?
The offset, yeah, so it's how many bits you need to essentially address every single byte on your page. So if my page is 256 bytes, then I need 8 bits to be able to reference every one of those. So I need to point to all the values. So I need to be able to go from 0 to 255. Yeah.
So that whole thing right there, that 16 bits, that's the physical address, right?
Yeah, this thing right here. Yeah, so that's our physical address made up in 2 parts, the physical frame number and the offset. So now it says the page table entry size is 2 bytes. That's good. So these are 4 bits right here, the permission, and now we know this physical frame number is also 8 bits. And then we know that the total thing is 2 bytes or 16 bits. So how large is this, is the process ID? Four bits.
One byte? No, it's half a byte.
Half a byte. Or, isn't there a name for it, a nibble or something? Nibble, there we go, it's a nibble. So, that's such a stupid name. So yeah, so we have a nibble for our process ID, so that means we can essentially, the maximum number of processes we have is 2 to the 4, so that's how many different processes we could have. What's 2 to the 4? 15 plus 1, that's a roundabout way to get to it. So 16 processes. Max. Okay. Now it says, what is the maximum size of the swap area that is supported? Well, so it says that, because it's a bit weird, the physical frame number should be interpreted as a swap location. So there's going to be up to 2 to the 8 entries because there's 8 bits in our physical frame number. And then each of these would be a page. So a page is also 2 to the 8. So 2 to the 8 times 2 to the 8 would be 2 to the 16. 2 to the 16, as long as I can do math, so that's like 2 to the 6 kilobytes because 2 to the 10 is a kilobyte.
So why do we multiply 2 to the 8 bytes?
Sorry?
Why do we multiply 2 to the 8 by 2 to the 8?
So this is the page size. And then this is the number of swap entries. So yeah, 2 to the 6 kilobytes would be 64 kilobytes.
Sorry, can you explain why 2 to the 8 is the number of swap entries?
Because it says the physical frame number should be interpreted as a swap location. So there's just 2 to the 8 possible swap locations.
And then the second 2 to the 8 is?
The page size.
Okay. So we need to include that as well.
Yeah.
And then what is S then?
What's S?
It's like a single.
Yeah, so it's a bit in the page table entry that just says whether or not that virtual address is currently in swap.
Currently in swap?
Yeah, its page is in the swap space.
Okay, so it's like 1 or 0.
Yeah,
Okay.
yeah, it's just a bit.
Wait, so is swap space in a disk?
Yeah, it'd be in the swap file.
Wait, so how are we sure that the swap entries is 2 to the 8 though? Because wouldn't we have, oh right.
Just because it says, yeah.
When you say amount of physical memory it can support, it's all of the levels added up.
Sorry?
Like when you say the amount of physical memory it can support, be like the
No. So the memory it can support is just how many different bytes you can address. Physically, yeah. Yeah.
So we're saying we have 2 to the 16th. We need to have the swap area needs to be 2 to the 16 bytes in size, right?
Yeah.
And then now you're just converting that to kilobytes.
Yeah.
Okay.
Yep. Yep. So it's just converting. All right. Processor supports a limited number of physical memory. No crap. As a result, okay, this is where it gets really weird. So page tables in 4 processes are packed into a frame. Yikes. So this doesn't quite have our trick. So this is not multi-level page tables or anything. So what it's saying is on a single page is actually 4 page tables. And then you have to figure it out yourself. So here it says process 5 would use the second chunk. If you actually went to implement it, it would actually be a disaster. But I guess since we're writing it on paper, we can roll with it, but it's kind of weird. So then it says, what's the maximum amount of virtual memory that is available to each process? So this is where it gets a bit weird. So each frame or page size is going to be 256 bytes. So that means we divide it into 4 because each of these has 4 page tables, which is kind of weird, which means if we have this, we have 64 bytes in our page table. Yeah, 1 page table is 64 bytes. So then it says, what's the maximum amount of virtual memory that is available to each process? Well, 64 bytes. That is the same as 2 to the 6? No, yeah, 2 to the 6. So we could have 2 to the 6 entries.
And this is assuming byte accessible memory, right?
Yeah, we'll always assume byte accessible memory. Yeah, so this will be 2 to the 6, or did I screw up the division? Packed in a frame. That's right, okay. Was the maximum amount of virtual memory that is available to each process? So it essentially would be that times 2 to the 8.
Okay, so it's 2 to the 6 memory addresses and then 2 to the 8
In the virtual page number.
page numbers.
Yeah. Wait, 1 sec. Oh, sorry, I messed up. Yeah, that's where I messed up. Oops. Okay, so I messed up. So that's how many bytes are in a page table, but yeah.
I was just going to say, like, isn't each page table entry 2 bytes?
Yeah, that's where I screwed up. Okay, yeah, so there's 64 bytes in my page table, and then I forgot to keep track of my page table entry size. So it's 2 bytes. So that means that if I have 64 bytes in our page table, and my entry is 2 bytes, that means I have 32 entries in my page table, which is why I thought I messed up, 2 to the 5. So then, to figure out the total amount of virtual memory, it'd be 2 to the 5 times 2 to the 8, which would be our page size, which is 2 to the 13, which would be 8 kilobytes. Okay, then it says, if the processor uses 64 bytes for the TLB, what's the maximum number of TLB entries that can be stored in the TLB? This is where we will go into the land of completely implausible. So this is the maximum. So we have 64 bytes for our TLB, which is also 512 bits. Why am I doing bits? Well, they want to make it difficult. So in their TLB, each TLB entry, the virtual page number, we figured out how many bits that is. So this is 5 bits. Then the physical frame number would be 8 bits. Process ID is 4 bits. And then all the permissions here are also 4 bits. So if we add that all up, how big is our how big is our TLB entry? 21 bits, which is, yeah, so it's essentially going to be 16 plus 5. So it's 21 bits, which is how you know this is not feasible to implement. So it's saying the maximum number you could theoretically fill out, but you couldn't implement this on. You could implement this, but it would be a disaster because you'd have to shift bytes all the time or shift bits all the time, and it'd be kind of terrible. But I mean, you could do it if you're super space constrained. So this is like 24.3 or something like that. So we'd have to round down. So we could have most 24 TLB entries max. Okay, weird question.
Where's the 21 from?
The 21 is the size of the TLB entry here. So 5 plus 8 plus 4 plus 4.
Okay, and then you're taking the.
Yeah, I just changed it said 64 bytes for a TLB, so I just changed it to bits. So 512 bits divided by 21 bits, you have to round down. So I could fit 24 entries if I really wanted to. Again, kind of weird question, but this gets to the hard part. So you get just a big old memory dump here, everyone's favorite. So it says, the following frame is used to store the page table for processes 0 to 3. Use an outline to show the location of the page table for process 0. So this is like a weird thing where it gets divided into 4. So process 0 is going to be the first quarter of this. Yeah, so the first 4 rows. So if we, so the whole thing here is going to be 512 bytes or 556 bytes. And then we're using this weird thing where page tables of 4 processes are packed into a frame.
I see. Okay. So you're just dividing the whole frame, which has 4 page tables on it, into 4.
Yeah. So this is a frame. This is one frame, and it's going to have 4 page tables. So you assume they go in order. So this is the page table for process 1, page table for process 2, page table for process 3, or 2, page table for process 3. And you can go ahead and sanity check yourself because we said each of them is 64 bytes. So there's 64 bytes or also 32 entries. So there should be 32 entries here. Each entry is 2 bytes. So luckily, see how they wrote that out? Each one of those things are 2 bytes. So along the top, there are 8 entries, and then we have 4 rows. 8 times 4 is 32, which is the number of entries we said before. So process 0 has 32 entries here, and these are what they are. So now it says, using the table above, translate the virtual addresses shown below for process 0 to their corresponding physical address. For each address, show the corresponding page table entry and the physical address. If the virtual address is invalid, write fault. If the PT is not valid, write invalid under the physical address. If the page is in swap, write swap X, where X is a dislocation. And you have to figure out, we have to do it in binary. So swap is the top bit of the first hex character. So luckily enough, so let's just divide it. So we know our page size is 8 bits, which is going to be 2 hex characters. So we don't have to write this out in binary, thank God. So we can draw a line here. So to the right of the line is the offset, and to the left of the line is the virtual page number. So the virtual page number is just the entry, so you just count however many entries. So they give you the first one, so it's the virtual page number at entry 0 or 1. So this is entry 0, this is entry 1. So this would be your your page table entry. And then to do the translation, this bit, the least significant bit, is a 1, which means it's valid. So the least significant bit is the valid bit. So basically, if it's an odd number, it's valid. So we know it's valid, so we can go ahead. This is just which process it is. Luckily, it lines up with the process. So then we would just, the 54 is the physical frame number. So we would just take that into the physical address, and then we keep the offset the same. Yeah.
Quick question. So inside the page table itself, like why are the inner values 4 hex values when it's an 8-bit offset?
Sorry?
So why is it like there's like 0, like 7, 8, 8, 8, like why is it 4 hex values?
So there's 4 hex values because they're 2 bytes. So this table is really weird because it only shows essentially 8 entries at the top, and then on the left are memory addresses, and they are not related. Well, they're kind of related because this would be, if these were all memory addresses, you'd have to multiply each of those by 2 because there are 2 bytes there. So it's a bit weird, and it's kind of, I guess, meant to throw you off, but it's kind of an unclear table.
Wait, so technically they're supposed to be like 16 bytes across. Is this kind of what it is?
So there is 16 bytes across, which these are all memory addresses on this side.
Oh, I see.
But at the top, but along the top are just the number of entries, which is unrelated. So if we count the number of entries, this would start entry 8, entry 16, entry 24. If we just counted the number of entries, which is the number of 2 bytes.
So the first entry is actually an address like 2.
Yeah, so this entry for element 1 is actually at location 2. Because it starts, each entry is 2 bytes, so you'd have to multiply it.
Oh my god, okay.
All right, so next one, virtual address 15. So you would think by looking at this, you know, oh, we take the 1 and then we take the 5 and it's this one. Well, it's not because, you know, again, memory addresses on the left and then just random entry numbers on the top. So easiest thing to do, 15, if we split this out, this is actually entry 21 if we write it out in decimal. So this is entry 16 here. So 16, 17, 18, 19, 20, 21 is this entry. So this is entry 21. So the page table entry is AC03. What?
Wait, so those, the left-hand side is not of the virtual address. That is the entry number?
Yeah, that's the index number. So
Okay.
yeah.
It doesn't represent the address on the page table.
No, it is the virtual page number, which is essentially the index.
Okay, so that's just like the number of entries in.
Yep. It's number odd, so it is a valid address. So we just go ahead and translate. So we take the physical frame number, which is AC, and then we just add the offset from the virtual address. So it would translate to address AC B4. All right, next one is a trick. So it is virtual address 20, which would mean it's entry 32. And there are only 32 entries, and we start at 0 because we like computers. So it's not even a valid entry. The last valid entry in the page table is going to be 31. This is asking for 32. So it is outside of our range, so it is invalid. All right. Next one is entry 5, so we can just count 5. Huh? Oh, sorry, I'm supposed to write fault, yeah. Fault. All right, next one is entry 5. So 0, 1, 2, 5. So it would be this one. So DB08. All right, and this one, the valid bit is not set, but the swap bit is set because it's the most significant bit in the last one. So 8 is 1, 0, 0, 0. So this means it's in swap. And it says to just use the physical frame number as the swap location. So you just write swap dB. Now next one is A. A is 10. So this is 8 here. 9. This is entry 10. So it was, what was it? 030E. Oh, now E in binary is 1110. So it means the swap bit is set again. So we just write swap and then use the frame number, which is 03. Yeah.
Does swap mean that it's in the TLB?
No, it just means it's on disk.
So if you don't have it in TLB, it's necessarily in swap? Or it just doesn't exist, I guess?
It could be swapped out and there's just a still entry there or something like that.
What does that mean? Like there's nothing there?
Like the entry could be there, but now it's what page it goes to isn't actually valid anymore. So you'd have to flush it or something. Yeah.
So, like, when you swap, you have to go to disk.
Yeah.
Would you ever go to, like, SSD or memory?
So you're swapping things out from memory, but you could go off to like an SSD or something.
So when you say you want to swap, it's always just swapping something into the TLB.
No, so this is where the page is. So this page here is in the swap file somewhere at entry 03.
So the page is not in the TLB.
Yeah, the page is currently on disk. So this means it's currently on disk. Yeah.
So for the first two words, a valid physical address, is that in the TLB?
May or may not be.
Can you tell?
Not yet. The last question is about the TLB.
So if the swap bit is 0, all we know is that it's either in the TLB or in like the raw memory.
If the swap bit is 0, it could just be a valid entry and it could just already be in memory.
So that would be like in raw or the TLB, right? One of the two options, or
It'd just be in memory. Like, yeah. All right, last one is 1E, which is entry, like 30. So it's the second last one. So just to spare some counting, it is this one. So it is, the page table entry is C607. So in 07, it is 0111. So which means it's valid, and so we just do the translation. So it would be C6F0. All right, last one quickly is like, hey, here's the current contents of the TLB. Assume that the TLB doesn't miss or anything. So let's divide them up. So we know that this is the virtual page number. This is the physical frame number, and this nibble here, this is the process ID, and these are all the permissions. So we have to check everything. So first, process 1 reads from virtual address 0, like virtual page number 03. So we actually have an entry here in our TLB. But if we look at the process ID column, it's a 0, and this is process 1. So it's actually not in there. So this is just a miss because it's the wrong process. For the next one, we check 19, which would be this one. So it's the correct virtual page. It's the correct process that also matches up. And then we check the permissions. So in this permissions, it is 6, which is even, which means the valid bit. If we go back here, the valid bit is 0. So it is a miss because it was invalid. And then quickly, the next one is 1D for process 0, which is this last entry here. So it maps up the permissions, it's valid, so it's actually a hit. It doesn't even say to give the address, but if we were to translate the address would just be EE49. And then for the last one, which is the most annoying one, is going to be process 0 writes to address 1B. So if we look up, that would be this entry. So the virtual page number lines up, it's the right process ID, and then we have to look at the permissions. So 5 is 0, 1, 0, 1. If we look at this permission table, that means that that O bit is 1, which by looking at this, it means it's read-only. So this one says process 0 writes to that address. So it's not allowed to do that, because that bit's is 0. So miss. Permission. Kind of annoying. Yeah.
So the TLD fundamentally is kind of like almost a lookup table to tell you whether or not the physical address that you're looking for is in the memory.
Yeah, it's basically a cache for page table entries.
Right. So it's just like where is stuff.
Yeah, it's just a cache. So it'd be way better if it was for a multi-level page table, because then it would save you going multiple levels. But for this, it's a single level, so it's just faster. The page table entry is already there instead of doing a separate memory access for it. Yeah. The first one is a miss because it would correspond, the closest page is this one, where the virtual page number lines up. But the process ID for this one is a 0, and it says process 1. So it doesn't line up, so it's not valid. Okay, sweet.
What if it's a read? Like, isn't there a thing where like you could read from other people's pages if you're not touching it other than just reading?
Yeah, but you shouldn't have access to just random memory.
Oh.
What about if I can like read your bank account or something?
I thought it would be, I don't have any money.
Okay, what about read your bank account in 10 years? All right, well, just remember, pulling for you. We're all in this